Okay, we're going to continue ionization energy. This will be hopefully a fairly short section. Just to kind of review the trends, remember on the periodic table, as you move up or go to the right, up a group or to the right in a period, metallic character decreases. Because remember, it's more metallic to the left and down. That means up and over will be, up and to the right will be less metallic. The radius decreases, and the first ionization increases. And I told you for the radius to also kind of remember, imagine like a little diagram like that as you get smaller and smaller. And then as you go down, you're adding another shell and so forth. Okay, well anyway, here I'm doing a problem that's kind of like number 4 on the ionization energy paper, okay? And I'm not going to do the exact problem. It's a good puzzle that you need to be able to figure out on your own how to do it. But I made up some numbers that are not true for these elements. But we're going to say, pretend this is IE1, IE2, IE3, and IE4 for these elements. For cesium, strontium, and barium. And what I want you to do, cesium, strontium, and bromine. I want you to tell me which is which on the chart. Okay? Okay, that's what they do on the paper. Well, this is a little thing that happens a lot. It pops up in different forms on AP, so I want to show it to you. What I would do, number one thing I would do, I would write these elements kind of in the way that they are on the chart. Like if you look on the chart, bromine is here. And I move over, strontium is there, and cesium is even down below. So cesium, strontium, and bromine. So cesium is here, we'll just say strontium above it, and Br is like over here. Bromine, strontium, cesium. That would tell me right off. First of all, I don't know if you can even read that. It's so small. What a bad thing. Can it fit down here? Cesium, strontium, bromine. Is that better to see that? I guess it is. You can't even see the cesium, strontium, bromine. First of all, as I go up and over, you would think, well, bromine should have the highest first ionization energy. So you'd predict 300, 800, 1100. Oh, that's got to be bromine, you'd say, because it has a higher first ionization energy. But then the thing would be, well, which one of these is strontium and which is cesium? Well, there's an interesting little trend that makes sense related to the charge of an ion and its ionization energy. Okay, and I'll show you what I mean. Cesium makes a charge of Cs plus 1. Hopefully you know that it's in group 1. Strontium is Sr plus 2. Okay, now if you think about the electron configurations, I'm not going to write them down for them, but I'll let you just kind of figure on your own if you do this. For strontium, it would be krypton 1, 2, 3, 4, 5s2. And for cesium, it will be xenon 6s1. All right, 5s2, 6s1. So, you know, strontium, as it forms a positive 2 charge, it's going to lose both of its 5s electrons to become isoelectronic to potassium. Okay, so think about this for a minute. It will lose 2 electrons, and that will lose 1. Cesium will lose 1 to become isoelectronic to xenon noble gas. All right, the point is, one of them has to lose 2 electrons, and one has to lose 1. So what that means is, look at the numbers for strontium, well, for what could be strontium. First electron, let's just say 300. Think about $300, like the tooth example I talked about earlier. Second electron, take it away, goes up, $900, okay? Third one, 15,000. Wow! 900 to 15,000? Look at that amazingly big jump. Then it goes 1,500. No, so not as big from there to there. 800 to 12,000? That's a massive jump. $800 for tooth number 1, 12,000 for number 2, then 12,800. That's not too big there. So what it says is this. To lose electron number 1 and number 2 seems to be pretty easy for this element, but it would hate to lose number 3. Or how about this? It would be very difficult, unstable. All right, so think about this. After you lose 2 electrons, which one of these would be in the noble gas configuration? And that will be strontium. Strontium will lose electron number 1, because it said it was 5s2. So losing one will be 5s1, losing that one will be 5s0, and now it will be just like, what did we say? Is it strontium would be just like krypton? Yeah, it would lose 1, 2, then become just like krypton. Isoelectronic with a full shell, it will be 4s2, 3d10, 4p6. So that whole shell will be full now. So that, remember, that's stable once it's isoelectronic to a noble gas. So now you'd have to be taking it away from that inner shell. So if you had to do an essay to talk about that, you would say after losing 2 electrons, strontium would achieve a pseudo-noble gas electron configuration. So it would be much more difficult now. In that stable form, it takes much more energy, more difficult to take away an electron from its level 4. It will now be taken from level 4. These two came out of level 5. That will be harder. It's harder once it achieves a noble gas, pseudo-noble gas electron configuration. It's harder to take away the electron. It takes even more energy. So that's all you would really need to say. Okay. Now for cesium, after taking 1 electron, it jumped pretty big. So that would likely be cesium. But also, process of elimination, you can kind of figure it out. So that's how I would do number 4. Arrange all the elements the way they are on the chart and look at it. And, sometimes they're not perfectly lined up, but you ought to be able to figure out most of the big ones, and then from process of elimination, all the others. So, and the way that comes out as an essay sometimes is, why is the change between the IE2 and IE3 of strontium greater than the change between IE1 and IE2? That's usually what they would ask. Because here, it's just taking away the outer shell valence to become isoelectronic with a noble gas. Once you have a pseudo-noble gas electron configuration, it is much more difficult to remove the electrons. And you can also, if you wanted to, you can even say the atom will be smaller. Because you strip off those electrons, it will now be smaller. In that pseudo-noble gas configuration, is more stability, and so it will be even harder to pull the electron away, require more energy. All right, there is one more trend that I'll just mention quick, and it's called electron affinity. And, we really don't even need to say a whole lot about this at all. But I'll just tell you, it's like the opposite of ionization energy. Instead of pulling an electron away from an atom, some atoms are so small, like fluorine, for example, that it will gain another electron to become F-1. It gains an electron to become F-1. So it's like fluorine gas plus an electron gives you F-1, gaseous. So the electron affinity is the amount of energy involved when one electron is gained by an atom to make, whatever, like EA1, EA2, and all that. And the electron affinities pretty much do the same thing. A smaller atom has a greater first electron affinity. But there are a massive number of exceptions to this, and so I pretty much leave it off, and I don't talk very much about it at all. But you should just know it's the energy involved when an atom gains electrons. Like, for example, some atoms, it talks about most atoms have negative electron affinities. It's exothermic. When an electron falls to join by the nucleus, it comes down like a ball falling to the ground. It's exothermic. So most electron affinity values are negative, as you see here. Like sodium, negative 53, and then fluorine, negative 322. And it makes sense. Sodium or fluorine, which one is more likely to gain an electron? If sodium gains an electron, it becomes Na-1. F gains it, it's F-1. Who's more likely to be more favorable? Who has a more favorable electron affinity? Who's more likely to gain that electron? Well, obviously fluorine, because fluorine will form -1. And look at all the energy released, 322 kilojoules when a mole of fluorine becomes F-1. Sodium is a metal that wants to be +1. It doesn't want to be negative. But isn't it interesting? It's like if these were two guys and that was a girl, if fluorine's not there, if sodium's like the last person alive on Earth, and Miss Electron comes up, yes, they will join and make sodium -1, sodium ion. Isn't that amazing? Only -53. So that's a neat thing about it. But I don't think I'm going to say a lot more about it. And then there's an exception. You know what? I don't even really want to talk about the chart. It just says the major exceptions. That nitrogen has 0 electron affinity and chlorine is greater than fluorine. But this little list kind of tells you from low to high electron affinity, Cosieber fickle. But you know what? You're not going to see it on the AP. You're not going to see that. But I think it's just good to know what electron affinity is. I can put it as I want you to know what it means, but that'll be about all. On your worksheet, there was a little section that asked you to write equations about write an equation, calculate electron affinity for beryllium. No, we're not going to calculate them. Write an equation, electron affinity. Okay, let me just see here. Oh, refer to the chart number 4. I don't know exactly what they meant here, but I just wanted to just tell you about this. How would you write these two equations? I'll just do them for you both. The electron affinity and hold on a minute. This might be better. Write an appropriate equation for the first electron affinity and for the first ionization of chlorine. Include the delta H symbol with the number, unit, and sign. Let me just do this for you. Number 7 for chlorine, letter A on the worksheet. What would be the equation for the first electron affinity of chlorine? Atomic chlorine means just Cl. First electron affinity would mean chlorine would be a gas. It would gain an electron, and it would become Cl, still gas, -1. And the delta H would be the electron affinity. It says for chlorine, electron affinity is -348.7 kilojoules per mole. So that's like a little thermo equation. This is only something for AP. Just you can write that one down. So an atom in the gaseous state gains an electron. Well, it's actually 1 mole of atoms gains 1 mole of electrons to make 1 mole of Cl negative. There's the answer. Now for the ionization energy, you start with Cl gas, and you would just turn right into Cl gas plus 1 plus an electron, and the delta H, the ionization energy, would be positive 1255. And when they give you the answer key, you can look at the other two. You can try these if you want. I'm not going to check them. And you can even try these down here. But you can look at them when you see the answer keys later. It's just sometimes you might need to know that this represents an electron affinity, gaining an electron, and that represents releasing an electron. Now, if, this is the answer, okay? If it had been Cl -1 and they wanted the first ionization of that, then it would just form Cl, okay? If it had been, for some reason, Cl plus 1 and you lost another electron, it will become Cl plus 2. So you just got to make sure your charge makes sense when you're either gaining or losing an electron. It's not a hard thing, but I feel like knowing how to do this will help you with it might help you with a multiple choice somewhere on the AP exam. All right, that's all I wanted to add in. So we are finally done with all periodicity. And yeah, there are all the trends right there. So I'll see you.